George?
Yeah, if there are no other questions, I just wanted to go over some closing remarks, if you would indulge me for a few more minutes. So let me share my screen, actually. The goal of the workshop was essentially to highlight this is an emerging interdisciplinary area of research, which really has a rich application potential. And it spans, I mean, as we saw during the day, I mean, it spans areas from mathematics, robotics, computer science, numerical analysis, and so forth. And so it's really, it's really rich, and applications as well. I mean, and it's really rich and it's emerging, and so it's worth pursuing. And so the various aspects of multi-agent behavioral analysis that we discussed today were along different lines. For instance, remote sensing and perception of multi-agent systems, like we saw in the morning when Andrea Caballero was talking about multimodal sensing and learning in the context of partial overlap of modalities during training and testing, and its application to multimodal dynamical scene understanding and target tracking. And then we also saw Guillermo Gallejo's talk. He discussed these event-based sensing modalities and their application to multi-agent scenarios, such as autonomous driving and SLAM and surveillance. And then Aljoša Oshep, he addressed the issue of dynamic scene understanding and object tracking in the open world setting, which is actually a long-standing open problem in machine learning, but is especially acute in the multi-agent system setting. And then there's also another aspect that was covered, which was learning and controlling the collective behavior of multi-agent systems. And that was Annie Shea's talk. I mean, she talked about the application of neural ordinary differential equations to the problem of learning and representing swarm dynamics from observations of individual agent trajectories. And we just saw John Barris's talk. He discussed this novel approach based on the mathematical framework of the Port-Hamiltonian formalism to learn and model the governing laws of autonomous multi-agent systems, both engineered and natural. Also in that vein, Isaac Kaminer and Abe Clark, they highlighted the problem of optimal control of these large-scale autonomous systems under explicitly adversarial conditions, and specifically the probabilistic destruction of agents. And this is really relevant to a large class of adversarial multi-agent autonomy situations. And then we also had some talks on situational awareness for multi-agent systems. Stephanie Gill talked about the issue of robustness and reliable information exchange for multi-agent coordination algorithms and how to defend against external adversarial influence in that setting. And Jonathan Howe gave an overview of his most recent work on collaborative SLAM and reinforcement learning for multi-agent systems, providing possibly an insight about how knowledge of the internal coordination and control of a multi-agent system can be helpful in discerning the behavioral patterns of such systems. And also on the numerical analysis side, Herbert Until gave a really nice talk on this, the statistical framework for solving certain inverse problems for physical systems, in particular the Bayesian inverse problems. So sort of opening the door to the application of these methods to infer the dynamics of particle swarms and related systems. So in conclusion, I mean, I would say, well, sensing and analyzing the behavior of multi-agent systems is very challenging. Perception modalities and algorithms need to be adapted to the multi-agent settings. So there's quite a bit of non-trivial work there. And also understanding the collective dynamics of multi-agent systems requires really novel approaches and novel understanding. And so, of course, many open questions remain. So, for instance, what is the proper representation of collective behavioral patterns? How to understand and analyze collective intent? How to leverage multi-agent control laws to infer and modify multi-agent system behavior. So all in all, you could say, well, this is an emergent area of research, needs a lot more attention and work. And so on that note, as future plans, as organizing committee, been thinking about following up with a journal special issue on this topic. So stay tuned. We're still exploring options, but we're hoping to be able to announce something soon, probably for later this year. So we would be soliciting contributions and also perhaps following up with workshops at other venues, in particular interdisciplinary, not just robotics and so forth. I would like to thank my organizers for the joint efforts to make this workshop a reality. It was really a lot of fun working with you all, and many thanks to all speakers for the fascinating talks throughout the day. And thanks everyone for attending and participating, and I hope to see you all soon and ideally in person. On that note, I would ask if anybody has any last minute comments, feedback, additional impressions. I mean, we have still some time. So feel free to chime in.
There's one problem I want to bring to attention to everybody, which is that multi-agent systems, they change their behavior. So, and if you have humans, if you observe them, they change their behavior. It's a very well-known phenomena in terms of taxation, that because you're going to be taxing, you're going to be taxed, you change the way you do your economics dynamics. There's problems in urban traffic control, where because there's interaction between the cars and the intersection controller, that people change their behavior and so on and so forth. So the problem has a closed loop that is very difficult when these things happen. As you observe the multi-agent system, the behavior changes. And if they are intelligent enough to find out you observe them, then it's even harder. Okay, so that means if you have humans in the loop or human-operated machines, we have looked at this, but that's another talk. We found that if you try to analyze this phenomena, you have to actually do different probability, completely different than Kolmogorov. Classical Kolmogorov doesn't work. And there's now results from mathematical psychology that emphasize this particular problem. Now, there's so much interaction between observation and control that you have to take into account. You can't do the standard control theory, sense, decide, actuate. Okay, it doesn't work. Anyway, just for those of you who are very ambitious for difficult problem, good luck. I've been struggling with this problem for 30 years, still have not been able to get a lot of done.
So this is more like cognitive systems you're referring to that could respond to being observed. So they behave sort of in like a quantum way. I mean, if you tamper with them by observation, they change.
I didn't say it, you said it. The mathematical probability is exactly the same as using quantum mechanics, but not because you have quantum mechanics. It has to do with the mathematics of the logic of events and all these uncertainties, and the fact that, let me give you one sentence. Every problem in multi-agent control, in stochastic control, starts by the following mathematics. Let X, Y, Z be a probability space and a measure and a sigma algebra, okay? Who the heck gave you the right to say that this is the same for all agents? How did you do that without exchanging any data? Can you explain that to me? Because Kolmogorov theory says I take my data, I create my sample space, then I fit the distribution, and then I go to measure theory. But now you have several agents, okay? Every one of them have their own model. How do they agree to use the same probability space? If you find more than 5 papers in stochastic control and multi-agent systems that they talk about this, I'll give you a big prize. Or if you convince me that there is an answer. Anyway.
That's a good point. Definitely worth thinking about. But yeah, I get the idea. So
I thought Jonathan Howe's the reinforcement learning, but I don't think John was here for that. But the you had with the rock paper scissors, where you had adversarial agents that are adapting their behavior to other. That kind of touches on what you're getting at with the observer.
Yes. Actually, I know Jonathan very well. I know his work. You're right. This is close to what I'm talking about. Okay, and it has extremely important applications in defense when you try to use, let's say you are in a sensor system, some of the sensors are automatic, others are humans in front of them, okay? How do they collectively decide? How do they agree? And, you know, there are mathematical psychological experiments with actual humans in simpler classification tasks that show that depending on the stress, meaning the time you have to decide, your level of knowledge or training, and the difficulty of the problem, classical or no classical so-called statistics have to be applied, okay?
So, but the question is, our engineered system, which do not include humans in the loop, could they be able to display this kind of behavior?
Yes, because the simple fundamental stuff is that if you have many agents observing and acting, it stands to reason that depending on the speed by which they infer and they control, there's an uncertainty principle, okay? That one agent does something, the other observes, in the meantime, the things have changed, and so what? Okay, this is the fundamental difficulty here is that in multi-agent systems, you have this kind of phenomena. There has to be, in the mathematics, a model for non-agreeable events. And you can try this Bayesian, but you get into a horrible sequence of who knows what and what I know when, which is well known in game theory, for instance, right? So the answer to your question, short answer is yes.
And that happens even if it's more of a physically based engineered system. In other words, one that doesn't necessarily have logic in it, not a hybrid type that you're talking about at one point, but let's say purely reactive, let's say particles.
Time is the important issue here. How much time you take to sense and do something versus actuate. If these are close, you get all this crazy phenomena.
Well, that's what I'm talking about. So you can think of a delay, a particle system with delayed communication. So you kind of introduce some delay, which could be constant or could be stochastic. But the point is that you're saying is that the magnitude of that delay could, mean in one case that the system could exhibit that kind of behavior, in other cases that it would not. So it's a critical parameter.
Right, and this is well known in biology, of course, because many biological systems, they use delay to good reason. We hate delay in controls, but some biological systems, they use delay because they want to take more time to decide. And this leads in simpler controls. But in engineering systems, it's exactly these delays between sensing and inferencing and control that they can create these uncertainties, therefore the problem. And this is not very difficult to imagine or even implement in a multi-agent system. Okay, it's almost the same as asynchrony. If you have asynchrony, you cannot have a global time. You have local time. You cannot have a global state because global time and global state go together. Fundamental computer science, right? If I have several local times, then what do? How do I deal with that? Okay, this is surprisingly unexplored, except for some areas of computer science under the name of distributed software hardware co-design. All right. The program is the collaboration graph in my model, and the communication graph is the set of processors. Okay, so if you try to do co-design of a program to be executed, then you can try to analyze that. I haven't seen anything else anywhere else, and I think it's important. As a matter of fact, You can even think about doing experiments to solve this phenomena in totally engineered systems, not humans. It's the multi-agent that causes, not so much. If you have humans and perception and cognition, then you get more.
Right. This is really counterintuitive in a sense, but very important.
Yes. There's an interesting inverse question. If I want to organize the swarm so they can decide faster, what communication architecture can I have? Because if everybody talks to each other, it's bad, right? You know that.
Yeah.
Because if you get too much data, you take a lot of time to decide and then you don't decide. Is that understood? The only place that this has been studied is in game theory, thanks to Aumann and his group in Israel. Okay, so all of these problems in multi-agent systems, it's fascinating. That I think they make common sense, but they haven't been studied. I guess they're difficult. Not I guess, I know they're difficult. Sorry.
Well, that's what we try to highlight here, but you kind of put your finger right on the spot, you know. So by highlighting, for instance, this aspect of it, I mean, I could think of other aspects that make it difficult, but they're kind of more obvious. I mean, this one is fairly non-obvious, at least for, you know, people like me. But then again, I mean, I haven't spent like 30 years trying to study those systems like you have.
But it's a very well-known problem you can have fun with, the so-called platoon stability problem in urban traffic, right? There must be more than 100 papers over the last 40 years in control theory about why the problem is unstable. And it's unstable because you insist on nearest neighbor communication. You explain to me how in wireless communication you can have only nearest communication. How do you do that? Because there's no links in wireless, right? They're waves. Okay.
Special protocols, but it's not trivial.
No. In wireless protocols, you get a wave. And the only way you create a link is because you keep only the packets that you have your address, the others you drop.
Yeah, that's what I call a protocol, I mean, basically. Yeah.
Fine. Now, we solved this problem. We solved the stability with my student Anup Menon, and everybody didn't like it because what did we do? We said, okay, we're going to do an expander graph where we allow communication for nearest of neighbors, okay? Which is easy in wireless, right? You drive on the highway, and in front of you comes a big truck, and you cannot see in front of you. Don't you feel like I have to give more distance now or something? You're not as aggressive, if you like, as if you just see 2 cars ahead of you, okay? So this is a very, very simple example of the importance of communication in these collaborative controls. Because I'm assuming when you drive in the highway, you try to collaborate, you try to hit each other, okay? So, but
it's not always cooperative, let's put it this way. If
right,
you've driven on the beltway
but the platooning program is cooperation. I'm trying to have a platoon and keep it stable. And there are many, many papers showing the instability of this by classical control theory. All of them use nearest neighbor communication. Okay. Anyway.
Well, I just want to keep digging into this. I think this is a rabbit hole that goes down a long way, doesn't it?
It absolutely does. Which again
underscores
underscores
do another workship soon. So
that's what I was saying. This underscores the importance of having another. I mean, following up with another workshop or two, because we have to keep the conversation going. Apparently, there's even a lot more than we have, you know, initially imagined and envisioned. You know, so
you don't know the kind of worms that you guys opened. Okay, I mean, seriously. There's all kinds of things in this that we don't understand, and yet people formalize them and do, etc., etc. Okay, all right. So.
Okay, so at least me, I'm gonna say goodbye, and I just want to join George, thanking everybody, speakers, attendees, and co-organizers.
Yeah, thank you very much, Eduardo.
Hopefully we organize another one soon and in person. And then this discussion, we do it with beers because it's 6 p.m., right? So, And then the hugging that I started the workshop now of topic talking about the hugging, then we hug again. Okay,
Yes.
good night, all of you.
All right.
Bye-bye.
Okay, everyone.
Bye, everybody. Thank you.